Okay, let's finish out chapter 2 with an example. So number 33 from the problems at the end of the chapter says a car is traveling at 20 meters per second and the driver sees a traffic light turn red. After 0.53 seconds, the reaction time, the driver applies the brakes and the car decelerates at 7.0 meters per second squared. What is the stopping distance of the car as measured from the point when the driver first sees the red light? Right, so our first step in approaching a new problem of any type is going to be what? That's right, we want to draw a picture. So I encourage you to go ahead and pause the video and draw your own picture. See what you can come up with, add all the details possible. You can even go into the writing down what we know as you're drawing this picture. Alrighty, so please pause now. Okay, I'm gonna trust you did that. So let's see, we have this car that's traveling at 20 meters per second. So cool, car, and we'll say it's going to the right, v is equal to 20 meters per second. That's all good. Well, then what happens? The driver sees a red light, right? So light suddenly turns red in this traffic box, traffic signal. So the driver takes a moment to react before the driver is able to hit the brakes. So the reaction time is sort of this pause here. Reaction. And then at this point, we can say that the driver hits the brake pedal. Right, so the brakes start here. And we want to know the stopping distance of the car. And the car is now decelerating, right? So I'll add my wheels in here. So eventually, the car is going to be able to come to a full and complete stop. V is equal to 0. We also know that while it is in the brakes region, it has an acceleration acting on it, right? It says the car decelerates at 7.0 meters per second squared. So that's telling us about the acceleration in here. 7.0 meters per second squared. Sorry, I dropped some sig figs there. Now, what's the direction of the acceleration? If the velocity is initially going to the right, but eventually the velocity stops, the speed decreasing, that tells us the acceleration, the direction of it needs to be acting opposite the velocity in order for it to slow down. Acceleration is going this way, and I would even add a negative sign. All right, so this is really good. We could fill in a few other things, right? Looking at numbers in the problem, and then I will stop sharing this so that the picture becomes bigger. It has this reaction time of 0.530 seconds. So I'll put that up here. Reaction 0.530 seconds. And we know that this is a reaction time, so I'll label that with a T. It's good to connect those variables so that they aren't too surprising. I think at that point we have all of the knowns. So what do we want, right? What are we looking for? Well, notice it says the stopping distance as measured from the point when the driver first sees the red light. So we're going to want some sort of X here as the stopping distance. Now I'm going to stop the share so that this becomes bigger. Whoops, sorry about that. Stop shaking it. Now that's the distance from when the driver first sees the light to when they start applying the brakes to when they do finally stop. And so what I'm going to propose is going to help us out with this problem is that we consider two different segments here, right? That we have a segment 1 that's from when the driver first sees the lights to when the driver applies the brakes. I'll call that x1. Sorry, that's really hard to see. x1, it's a little easier. And then the second segment is going to be from when the brakes were first applied to when the car comes to a full and complete stop. So we'll call that x2. And so our total distance x is going to be a combination of x1 plus x2. x1 plus my x2. And the advantage of breaking it up into segments like this is that there's two different accelerations here. Anytime you have two different accelerations, you're going to want them to be in different segments because our kinematic equations only apply to constant acceleration. So in segment 1, we have a constant acceleration. In segment 2, we have a constant acceleration. In segment 2, the acceleration is negative 7.0 meters per second squared. What about in segment 1? Well, in segment 1, it says the car is traveling at this constant 20 meters per second. So that tells us, it implies that the acceleration in segment 1 is equal to 0. That's some hidden information there, and that is an A. I'm sorry for the light being a little bit obnoxious there. All right, 0 meters per second squared. So just knowing this acceleration and that 0 and the velocity at any point in there is 20, we can figure out x1 very quickly, right? So we can say for x1, that's equal to my initial velocity times time plus 1/2 at squared. And because the acceleration is 0, this whole second term is going to go to 0. So if we plug in for x1 is equal to my initial velocity is 20 meters per second times my time, 0.53 seconds, plus 1/2 times 0 is just 0, then that gives us the x1 distance, right? Which you could wait to calculate till later if you wanted, but I'll check it now. So 20 times 0.53 is 10.6. What about the units? We have meters per second times seconds. That will come out to meters. So that tells us it's 10 meters before the driver's even able to hit the brakes. But what about once the brakes kick in? How much distance will the car cover during that region? Well, for that, we're going to focus on a whole different segment, right? So up here, we're focused on constant velocity, given time, given acceleration. For the second part, we don't have any time given to us, and we're trying to find displacement x. We know the final velocity is 0 because the car comes to a stop, and we know the acceleration. So we have these two pieces of information. We need a third in order to be able to solve for some factoids. And the key is one part of our reasoning strategy that said if you're dealing with motion in segments, remember the final velocity of the first segment is the initial velocity of the second segment. So for this case, when our car was traveling at a constant velocity of 20 meters per second, the final velocity right at this point is still going to be 20 meters per second. Sorry, that's a little small. That's the final velocity of the dark blue segment, but the initial velocity of the light blue segment. Call this my V0 in the blue typeface, the light blue, teal. Kind of greenish in the video. All right, so that is a huge help because now I know my acceleration, my initial, and my final velocity, and I'm trying to solve for displacement. So I just need an equation that does not have time. And we do have one such equation. So we know that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times x. This one has popped up a few times. We've also solved for displacement with it a few times, which is what we're going to want to do here. So we're going to subtract the initial velocity the other side and divide by 2a. All right. So this is all set up for us now. Here the acceleration is not 0, so we will get a real result, which is good and useful. And we can now plug and chug, being very careful to keep our final and initial velocity straight. And this is also, by the way, going to be my x2. X2 is equal to my final velocity, 0, because it stops, meters per second squared, minus my initial velocity, 20 meters per second squared, all divided by 2 times negative 7.0 meters per second squared. Right, now it's getting a little low and a little blurry. So hopefully it's focusing enough. Let me know if not, I can post a picture of this too. So notice the negative sign is on the outside of the square. So when I square this 20 meters per second, it still is going to be negative. That's not a problem in this case though, because we're dividing by a negative acceleration. So the negatives are going to cancel. We can double check it right now. So 20 squared is 400, divided by 2 and divided by 7, negative 7 and negative 20. And this comes out to 28.57. And that will also be in meters. And so our final result is just going to be adding these two together and getting the proper number of significant figures, which in this case is 3. So if we add those together, we should find that, oh, conveniently, I left that 28.57 junk all in here, so I don't even need to retype that. So plus 10.6, which that one was exact, and it comes out to 39.1714. With meters as my unit, so we'll double check the sig figs based on the problem statement of the numbers given. And the problem, each of the numbers has 3 significant figures. So that means I need to round to the 10th decimal place. So my final answer is going to be 39.2 meters. So that's half a football field right there. So hope that the drivers saw the red light well in advance. It's why you have to pay close attention when you are driving on the road. So that pulls us through all of chapter 2. As you have questions, please do ask away. I'm happy to discuss things further because there are some really interesting challenges here and it's really hard to go at it alone. So let's work together and we will figure this out.